Can you see the Jupyter page okay?
We can, yes. It's very small, so you probably want to zoom in.
Yeah, it's very small. Don't worry, don't worry. It's going to get bigger. Okay, these are my actual slides.
Ah, perfect. That's great. Go ahead.
Okay, wonderful. All right. Okay, so the link on the agenda is just a link to this Jupyter page where there's a bunch of folders. I just wanted to direct you to the fact that my talk is also a notebook, and you can find it in this NBs folder. I've left my binder open too long, so you you can't actually see it because it's shut down. But the notebook is called talk.ipynb. So if you want to follow along with the notebook, that's what you can do. Okay, so hi. Thanks, Lucas, for kind of segueing into this talk, where I'm going to talk about physics analysis as a differentiable program. And this presentation, is itself a notebook. So if I run that cell above, I'm going to get 4. And so that'll help us have some interactive fun. All right, so what I'm talking about today is, what does it even mean for analysis to be differentiable? You might sort of imagine what that could mean from the previous talk. But then why even should we care about that? And moreover, how can we differentiate, physics in the first place? Some of the libraries you might have seen already. And then we can see it in action with NEOS, which is an example implementation of differentiable analysis and involves machine learning. Oh my gosh, everyone's favorite thing. Okay, I'll draw you in at the start with this workflow that I penned by hand, because this is a Jupyter notebook, and you can't do normal slides. So from the bottom left, this is a typical analysis workflow, maybe, where we start off with some data, have some kind of cut flow. Then from there, we'll construct some kind of observable or statistic of the data. And from that, we build some statistical model. And using the likelihood from that statistical model, we'll build up this test statistic profile likelihood ratio. Then we'll do a hypotheses test and see where the new physics is. We'll get like a p-value or a limit as the result of this analysis. And so you can see that this analysis kind of has some free parameters, right? So those cuts are arbitrary unless we say otherwise. And that observable might be a function that you can parameterize. It could be something multivariate. We do that a lot nowadays, right? And so how do we optimize those parameters? Can we even? Well, sure we can, right? And here's what we might do. Maybe if we have a set of cuts, we'll do some kind of grid search, and we'll try and maximize this Asimov significance, right? Nothing new there. And then if we have a neural network, we'll just do gradient descent. We might like a really good discriminator between signal and background because it makes sense, kind of a sensible objective, right? But I guess the question I wanted to raise here is, why do these methods and goals of optimization differ if they are two things in the same pipeline, right? Surely they should have the same objective, and they don't have to differ necessarily. So here's a example. Thank you to Alex Held for this notebook, where it's a cut being optimized with respect to the Asimov significance, but using gradient descent, just like a neural network. And so to make this work in practice, we can't use like a harsh cut because it's non-differentiable, and so we actually have to spread the profile of the cut out a little bit. So it's not like 0 weights and 1 weights. It's like a continuously varying weight between 0, 1, and 1 applied to all events. And there you see it training and getting a pretty sensible cut value. And you can also, there's a paper there linked that uses the Asimov significance as a loss function. And so really these things are closer than we think. And so, from this, you might be able to imagine some kind of jointly optimized analysis pipeline with respect to a single objective trained using gradient descent, because, that's a well-studied method of optimization. And we have all this automatic differentiation magic. And so to do that, that kind of raises this question, right? I mean, like, what should that objective be? I mean, Asimov significance is good, and it's it's a very tractable and useful objective, but maybe we could do better. And there's some really nice insights into this if we have a look through this survey of deep learning and how it's applied to LHC physics. A great review by Dan Weitz and Dan Guest and Karl Cranmer. And so there's a passage here that says tools are often optimized for performance on a particular task that is several steps removed from the ultimate physical goal of searching for a new particle or testing a new theory. And then, that might make you think that like binary cross entropy, for example, could be an example of one of those things where, because it's not a p-value, right? And then another thing to think about is that, sensitivity to these physics objectives needs to account for systematic uncertainties. So you see things like the sculpting of backgrounds and, the setting for the nominal nuisance parameters might not be the best when you profile over a whole range of nuisance parameter settings. And so, just to summarize that, so we want something that's a goal directly related to our physics objective, and we want to take into account this, full profiling in order to be robust to all these systematic changes. But don't we already have this, right? It's at the top left of this plot. It's, we get our limits, so p-value out of the analysis, and that's what we want to improve. So, if we can construct a full analysis where we can back propagate through the whole thing, we can optimize, the median significance, actual significance, or with respect to that rather. So we can optimize our, these three parameters by taking the derivative of the limit and with respect to the cut and updating the parameters by gradient descent, just like a big neural network, if you want to think about it that way. Okay, so that's kind of cool. So this is what we mean by differentiable analysis. So an analysis with some free parameters that we can optimize end to end with gradient descent. And so there's this sort of update rule, right? We just move in the opposite direction to the gradient modulated by some learning, right? And so this is an example of differentiable programming, which is, another buzzword coined by Jan LeCun, which is sort of meant to be the superset of machine learning in that, we're not just dealing with one neural network here, we have this whole, pipeline that's differentiable. And so one thing to think about that we kind of saw in Lucas's tutorial is that we kind of have the chain rule to consider here, because the whatever we have to, whatever we take the derivative of has to backpropagate, through the entire analysis chain. And so there are a bunch of different derivatives that we actually have to think about in terms of can we actually evaluate them. And there's no guarantee that that's the case. And, so this slide can then be amended to, it's not just what should the objective be, but can we also evaluate its gradient? And so is every step of the analysis differentiable? And so here's an example, right? It's an example of something in HEP that's not immediately differentiable. So when we think about histograms, the heights of the bin don't necessarily vary smoothly if we change the data a little bit, right? Because the bins will just jump up and down in height by one if the event's in the bin or not in the bin. But this is a problem, right? Because updating the like the data distribution, or at least like a representation, downstream of the data, updating the shape of that is exactly what we do if we updated like cut values, for example. So we need this change to be well behaved. And here's just a bit of code that I'll run to show an example where we shift a Gaussian distribution to the right. We just vary the mu. And then we see what happens to the corresponding histogram, where we draw 100 points from that distribution and see what how the histogram changes. And you can see that the bin heights are kind of just jumping up and down, willy-nilly, however you like, but not in a nice sort of smooth way. And so this is something we want to amend here. This is the kind of derivative we care about. And so one way to remedy that could be this thing called kernel density estimation. And that formula might look a little bit ambiguous. All it really is, it's a mean of some kernel function, k, centered on each data point, and then smoothed with this parameter h. And to give you a bit more intuition, what we actually do in practice is use a standard normal distribution for k. And then that formula just reduces to something much more intuitive. It's the mean of a bunch of Gaussians centered on each data point with some global width that we evaluate ourselves. We decide what that is. And so there's this one size fits all kind of modulation, and you can kind of think of it a little bit like the bin width, right? It's a sort of non-parametric hyperparameter in a sense. And so just to give you a little bit of intuition, here's the kernel density estimate on a set of data, which you can sort of see at the bottom. And this is what we have. This is what happens when we vary the width of all those little Gaussians. And it can kind of get crazy if you make it really big. And then right at the start, it's kind of like horrible and jaggedy. And so this is kind of interesting because the choice of bandwidth, really changes the KDE quite a lot. It's very sensitive to that, more so than the choice of the kernel function, actually, which is quite interesting. So say we have that, and then we want a set of counts from that, like in our Poisson statistics kind of way. Well, we can get that pretty easily, right? Because a KDE, since it's a bunch of Gaussians, it's got a tractable PDF, and so we can just evaluate the area under the curve for each binned interval, and this is what that looks like. And so here is a histogram of fixed binning on some data, and here's the corresponding KDE. And then there's the area under that KDE for each point or each bin, sorry. And that's a kind of nice kind of approximate histogram. And you can see that for really small bandwidth, it looks exactly like a normal histogram. And there's a bit of intuition there because that means that the bandwidth for each Gaussian is really, really small. And so it's basically like having a direct delta function at each data point, which is basically counting, right? Counting like a histogram. So it kind of makes sense. And so this is an idea of like a soft histogram. And so does it resolve our issue? Let's run this code and find out. If you're running this in the binder, you need FFmpeg to actually like display the movies inline. So there's like a little commented out thing that lets you save it and view it offline. And so you can see actually that these bins are moving pretty smoothly as we vary the KDE, which is really nice, right? That's exactly kind of what we want. Maybe we can do a little bit faster. Oh wait, no, the variables in the previous slide, I'll just leave it. But okay, nice. Here's one example of a smooth histogram. Or soft histogram. And here's another one. Be familiar to anyone who's worked with neural networks, right? This softmax function where we sort of just exponentiate the data points and then normalize them, which is gives you values between 0 and that sum to 1, which is really nice because that's kind of like spreading out that one event into many different bins. So it's not like the event is in one bin and it's not in any of the others. It's kind of like it's weighted in all the bins, and that's sort of the way to think about these differentiable histograms. And it's kind of a natural choice, right? If you have a neural network, because you can just slap this as your last layer, right? You can just softmax the output, and then if you do your neural network on an event-wise basis, you can then get like a contribution to a set of bins. On a per event basis, just like a histogram. So this is kind of nice. Okay, so histograms, fine. We can do those. Another step would be the likelihood function. That was in our analysis workflow. And thanks to awesome people at PyHEP, this has us mostly covered. Almost. There are some things we need to iron out in terms of everything in PyHEP being differentiable, but we can get pretty far with it. And yeah, so just a big thanks for the team because this step's kind of already done for us if we're using hist factory likelihood, that is. But then we hit a bit of a roadblock when we think about the test statistic, because this profile likelihood ratio, which you all know and love, has these things with hats on them, and if we have a hat, we normally have a fit, right? That's kind of how it works. And so when we're doing these fits, to do this kind of automatic differentiation, we have to unroll every single iteration of the fit at runtime, trace all that execution, and then backpropagate like all these millions of different iterations, which is computationally not really very nice. Okay, that's sort of the first bullet point here. And then another thing to think about is the actual number of iterations itself doesn't vary smoothly when you change the data a little bit. So that's kind of like another way in which this is not differentiable. How do we kind of remedy this? Well, we can use this thing called fixed point differentiation, which is kind of a nice thing we stumbled upon. So if we think about like a minimize or maximize routine, it has a fixed point when evaluated at the minimum. That is to say, when we initialize a minimize routine, it will return some converged value, x star. If we were to evaluate that minimize again at x star, we'd still get x star back. And that's what we mean by a fixed point. And we can do a bit of, we can kind of exploit this a little bit, because if a fixed point exists, we only really need to look at these converged iterations to actually, get the gradient information, because that's what we care about, right? We only care about how this optima or these optima sort of vary as we're sort of changing parameters upstream, and so we don't have to think about all these things at the start where it's initialized at some value and it kind of jumps around a bit, and that's not going to affect our final answer, and so this is kind of a nice way to get around it. And there's a little bit more information on this if you follow that link. And just to kind of put this back in context, what gradient was I talking about there, right? And so the shape of the likelihood, and also, of course, its maximum point, is implicitly a function of the yields used to construct the hist factory model. And what I mean by that is that, if we were to change those yields, of course, the shape of the likelihood would change. But, we don't explicitly write the likelihood as a function of those variables. And so, this is important because when we differentiate the profile likelihood, we're going to end up differentiating, the best fit values with respect to these yields at some point. So we want to know how how that maximum varies as we vary the model construction, because that's essentially the whole everything from observable construction to the profile likelihood. That's that entire derivative in the big grand scheme of things, right? So and then we just times it by how those yields vary with respect to whatever parameter we wanted to optimize. And so to try and internalize that a little bit, we can think about that moving Gaussian example where we change some parameter mu, which changed the shape of the likelihood, or the Gaussian just shifted it to the right a little bit, and then the histogram changed a bit. But we wouldn't write the histogram as a function of that parameter, right? It doesn't really make, even though it makes sense, it's not how we would write it. It's not an explicit function, and so it's the same thing. That's just to try and get some intuition. We can find the gradient of how these best fit points would vary with respect to those yields, but we don't write them explicitly as a function of those yields, and that's just kind of what we mean by implicit in this context. And so, okay, just to zoom out a little bit, put all this together. So using softened histograms and cuts, we can differentiate the sort of start of the analysis, all that data preparation and constructing the observable, and then thanks to PyHEP, we kind of get the derivative of our likelihood function sort of for free, which is really nice. And then if we hijack the fitting using this whole fixed point differentiation idea, we can extend that differentiability all the way to the profile likelihood and like the p-values that we get out of it, which is really, really nice. And so we kind of have all the ingredients, right, in theory, to like differentiate a whole analysis. And so what happens when we actually try to optimize it? And so this is where this whole NEOS things comes in, right? So initially it was named neural end-to-end optimized statistics, but the whole point is that we don't actually kind of need this neural network to do this differentiable analysis. So just changed it to nice because it is also nice. And then click through to that GitHub link to see the central repository and maybe leave a star, if you're feeling like it. And so, okay, NEOS is implemented in JAX, just like Lucas sort of gave you a really quick lightning tutorial on. I have an optional tutorial at the bottom there, which I don't actually have to do now. And so it's this idea, you just write your normal analysis code in NumPy, which is, pretty familiar. And then, those gradients kind of come for free in some sense, which is, really nice. So this kind of pads out all the little steps in between, besides these, big picture blocks. And then we also make use of this facts library. That team's been really helpful, which, sort of has this wrapper function that we wrap around this this fitting that lets us actually evaluate the gradients in the way I described, where we only look at the last, like the converged iterations. And so, yeah, thanks to both teams. All right, now to talk about, the Neos workflow itself. I got fed up with writing, all these slides are actually HTML, right? And so, because it's a Jupyter notebook and I can't format anything in a nice way. So I got fed up and I drew this slide. And so I'll just walk you through it very slowly. So this is the setup for this Neos problem. So we start out with 2 Gaussian blobs. We draw samples from both of them. I call one signal, one background, and they're kind of close together. So it's not like a trivial problem. And then from there, we create some kind of systematic variation, like an up and down setting, kind of like we might have in practice. And then we feed in the XY coordinates for each of those 4 distributions, every single point. We feed that into a neural network, and that's what we're going to think of as our observable here. And then so the output of that neural network becomes our observable. And then we use one of our histogram methods. It could be just a softmax at the end of the neural network, or we could be using like a kernel density estimate if we have like a regression network instead. And we'll get some histograms out, and then from there it's pretty smooth sailing, right? We just construct our model in the normal way here with one nuisance parameter, which is a histosis if you want to use the hist factory language. We do our fit, and then we get our CLS evaluated at the nominal signal hypothesis, and then we backpropagate that CLS value to update the weights. And so what does this look like? And here's a nice little animation to show what that looks like. So this is actually a slightly more simple example than I described in that slide, because you can see there's actually only 2 orange blobs and not 3. That's because just for this simple case, we're just taking we're using we have like an up and down variation of the background, and then we just take like the nominal as the mean of each distribution. And so we can see this is some optimization happening in real time. And so the background of that sort of a plot on the far left, that's the neural network decision function. It's the output, which is in this case it's 2 values because there are 2 bins, and we're using a softmax. And so as you can see, it kind of not only does it learn to separate the signal and background, it actually learns to wrap around the uncertainty, and it kind of does this trade-off between this not just signal to background ratio, but also the background uncertainty. Really, really nice behavior. This is what we mean by like systematic aware learning. And we see the model on the far right doing that trade-off, and the CLS value in the middle just going down per epoch, which is awesome. If we do something slightly more sophisticated than that, we use the KDE, and then we actually use that full histosis that I was talking about. We get like a similar result. It doesn't wrap around quite as nicely, but this time we have 3 bins, so a little bit more kind of a little bit more complexity and expressivity there. But the kind of gets harder to interpret. Just like differentiating between 2 classes, right? So it's a little harder to interpret the output. But even for this case, we can see that a 3-bin histogram is optimized, just as well, which is super cool. And that's pretty much the meat of the talk. And the kind of next that I just highlight is to actually release a paper on this stuff. Although the software, right as it is right now, is citable. Then to make PyHEP fully differentiable, as I was talking about before, and then maybe even making awkward array differentiable, because that it's used in like Kafir and all these other sort of IRISEP type projects, which would be awesome, because then we could really differentiate like a real analysis. Doing some more studies, making some more physics tools differentiable. And the kind of cool thing about all this stuff is that we kind of have an organization that's trying to target all this stuff now. So we have this thing called GradHEP, which is an effort to just consolidate all these efforts into one place, to build the differentiable analysis blocks, but then also, also to apply them and create like, common software packages and things like that. And so there's like a new differentiable computing HEP Software Foundation activity, which kind of encompasses all of this. And I've got a link to that page there, which lists a couple ways involved. And literally everyone is welcome to join in if this is something that you think is interesting, because it's a super early stage. And so just one last slide to give some thanks, some extra thanks to the authors of the Inferno paper, which is very similar to this work, a big inspiration. Thanks to people in IRIS-HEP for some nice support and discussions. Thanks to Lucas for being a great supervisor, of course. And thanks to the organizers and to you guys for listening. That's everything I've got to say.
Nathan, thanks a lot. That was really interesting. Thanks. So we're a little bit over time, but I think it would be a shame to cut so early. I think we could maybe take some questions. So I will stop your share, and if I can find the right place, I can start my share here. So yeah, quite a lot of questions about the kernel density estimation. So Jim asks, if you're using the KDE to represent measured distributions, does the choice of bandwidth relate to the choice of bin width in the histogram? And is there methods for choosing an optimal one?
Yeah, that's a great question, right? Like, how do you choose the bandwidth? It's a free parameter too. And so yeah, we're actually we're doing a couple studies at the minute to sort of investigate this, because okay, well, strictly there is some things in literature that give this quote unquote optimal bandwidth in terms of like minimizing the mean squared error with the true distribution, and you have to do some sort of like, there's an adaptive step where you do like a kernel density estimate of a kernel density estimate to get that. So that's a little bit complicated, but then the trade-off you kind of want to make. So you reference bin width, and so in terms of like how does it relate? Well, I mean, it relates in the same sort of way. If you have like too large a bandwidth, it's kind of like putting everything in one bin, in that you're kind of just like smearing out the artifacts of your distribution. But I guess in terms of gradients, that's kind of like another question. We'd actually want the bandwidth to be pretty close to the bin width, because if you can imagine, like a kernel density estimate sort of centered like in the middle of a bin, or one of the individual data points is centered in the middle of the bin, the kind of leakage into neighboring bins is kind of like optimal when the bandwidth is kind of on the order of the bin width or a little bit less. And so in terms of like representing the gradients in the like a true histogram, there's actually kind of like an interplay in practice between the bandwidth and the bin width, which is kind of interesting. Yeah, but we're still doing studies on this, and it's a very good question.
Okay.
Yeah, sorry, that was a bit rambly. Was that enough?
Well, it was a bit of a kind of watch this space. I think it clearly is an
yeah, a little bit. Lucas might also have something to say on that.
Yeah, no, I mean, I don't have anything special to add. You explained it very well.
Okay, thanks.
Yeah, and then there's a question from Hans. How do you treat the soft histograms in likelihood estimation, which usually assumes Poisson statistics in the bin, because the bin values of soft histograms are not Poisson distributed?
Right, yeah, so it's kind of like, I mean, yeah. So the, I guess, when we're using a histogram, it's kind of like doing some sort of density estimation, right? And I guess, yeah, a histogram is a natural way to describe Poisson statistics. But I mean, as you can see, like the kernel density estimate in the limit of quite small bandwidth actually gets really close to this. So I think there, you're right. There is a discrepancy there, but I don't think it necessarily matters that much. It's something I'm actually still thinking about in terms of like how accurate the model is. Because yeah, like I said, I guess we use that. We treat it, like a set of Poisson counts. So yeah, okay, it's a bit of an approximation, but I guess anything that smooths out something discrete will always kind of be a bit of an approximation. But it still works in practice.
Yeah, another way to think about it.
It's a big approximation.
Yeah. I mean, another way to think about it is that for evaluation, you can then always switch to the hard version again. So this is basically to optimize the analysis. Let's say your event selection is completely defined by neural network, and so you use that to optimize the neural network by additionally taking into account systematic uncertainties. But then once you have optimized it, you can still kind of resort back to the hard version and then just fill a histogram as you usually would, right? But it's just a tool to optimize the analysis.
Yeah, that's also a really good reason.
Okay, maybe let's just jump quickly to what Lindsay was asking. I think there's the same kind of observation about poor statistical properties, especially with sparsely populated data, and a suggestion using penalized basis splines, which might be an alternative.
Interesting. I'm going to have to Google that. But yeah, no, thanks for the suggestion. And yeah, I guess, the first question is kind of answered what Lucas said. Like, you don't actually, in practice, we don't actually have to use the soft histograms when we calculate our final, result that we put in a paper and submit to conferences.
Okay.
Yeah, but then you're throwing away all of the optimization that you're doing based on systematic errors and whatnot like that, especially when it comes to the tails. So it seems kind of at odds with itself.
I mean, not complete. If you go back to Nathan's animation with the blobs, I don't know if Nathan can pull it up quickly.
Yeah, I can pull it up if that's yeah.
Yeah, but you had let's say like the background, which has a big systematic uncertainty as to where exactly in phase space it's located, and basically what this trains you is similar to what kind of adversarial training does. It basically minimizes the uncertainty that is kind of associated with this uncertainty of that background, and so you will still, like, even if you switch back to the hard version, you will still retain kind of that thing, like that robustness that you learned. Right? You'll not kind of like the final CLS value will not be the CLS value of the hard version, but I mean some of that stuff you still kind of retain. Right? So here on the left hand side you see these three blobs, right? And the decision boundary wraps around them in the same way that maybe adversarial training would.
Very good. Okay, there's clearly we could talk about this for a very long time, but we're almost 10 minutes over time. But thank you very much to Nathan and Lucas for giving the introduction to this topic, and lots of comments in the Zoom chat, by the way, about people really appreciating this talk. And I'm very glad, Nathan, that you also gave the link to the new HSF activity area. So I think we have a forum for this moving forward for people who would like to be involved in
exactly
these really fascinating questions. But yeah, I think we will close the session here.